Okay, hello everyone, thanks very much for joining me. It's Ollie Epsom again, and today we are going to look at the Type 23 frigate propulsion system. This is part one of the presentation. Let us see what we're going to talk about. So, in this presentation today, we are going to look at the following. An introduction to the Type 23 frigate, so what is it, where do they operate, what are they for, why do they exist? We're going to look at the prime movers of the Type 23 frigate, which is the CODLAG layout. Now don't worry if you don't know what CODLAG means, you will definitely know what it means as a result of this talk. If you already know what it means, well, maybe you want to watch anyway. We're going to look in general terms, obviously, at some of the many noise-reducing features of the Type 23 frigate. And we'll have a look at the fuel consumption and performance of the platform. In future lectures, we'll cover these things in much more detail and go into the actual operation of the machinery involved. So we'll look at the electric motors and the power generation system, and we'll look at the gearboxes and the clutches, and we'll look at the gas turbine drive and the limitations of it. And we will look at some control system basics. Now, one of the issues I had when I was putting this talk together, as opposed to the Type 42 series, is that on the Type 23 frigate, because they are computer controlled, all the systems are interlinked somehow. So it's very difficult to talk about one system, say the electric motor, without actually referencing the power generation system, the control system, the gearbox system, the force lubrication system, and so on. It's actually much more difficult to get a differentiation of systems. So I've tried to be as focused as possible when I put this together, but there may be some bits where it's a bit complex. It's also worth noting that as a result of the computer control system, that old enemy of unexpected emergent behaviour can be a feature. Where you have mechanical control of fixed systems, that is less of a risk. I'll be describing the original propulsion system layout as these ships left the yards in the late 80s to the late 90s. So beginning in 2018, Type 23s are being radically overhauled in terms of the power generation system. Prior to that, they have been modified substantially, but most of those modifications were to the weapons and sensor fit rather than the actual power system itself. I think the general layout will be the same even on the modified frigates, but I don't have experience of those modifications, so I'm not qualified to speak to them. How can I give this talk in the first place? I served on a Type 23 frigate as a Deputy Marine Engineering Officer, DMEO, about 10 years ago. I was qualified to operate all the equipment that I'm going to talk about today, and I've tried to take care that the information on this talk is not classified, but it is hard to find. However, if you do have any comments or corrections, please feel free to put them down below. I'll not, as I've already said, be describing the newer overhauled power generation equipment because I don't understand how it works. So, Type 23s, what are they? Here is a picture of HMS Sutherland, which is one of the newer Type 23s. In this photo, she's appearing in her almost original spec with the Seawolf weapon system, harpoon, but she has been modified a bit by virtue of the Mod 1 4.5-inch gun being added on the front. So the Mod 1 gun came out in the early 2000s and it replaced the Mod 0 gun, which is from the 1970s. And the main external difference is that the Mod 1 has this faceted flat edges on the cover, which is supposed to reduce radar signature, whereas the Mod 0 had a round fiberglass cover. In actual fact, the major differences are inside the gun, because the Mod 1 is mainly an electric gun for aiming, training and so on, whereas the Mod 0 was mainly hydraulic. Nonetheless, this is a good representative picture of what the original Type 23s looked at. They were a class of 16 anti-submarine warfare frigates, entering service from 1990. Now, they were originally conceived in the late 70s as a cheap North Atlantic anti-submarine frigate. Something a bit akin to the Leanders. I'm not saying the Leanders were cheap, because the Leanders were really good, but something that would replace the Leanders in service. And as a result of the Falklands War, the design of the Type 23s was significantly modified, upgraded, extended, enlarged and beefed up, with the result that they became a relatively good general purpose platform, albeit with a very strong anti-submarine bias. And as we'll see throughout this talk, that anti-submarine concept really did drive the design of these frigates, even though they're not actually used that much for anti-submarine warfare in day-to-day existence. As I said, they were subsequently modified and updated once they were built, and so all can now perform better in a general purpose role, and quite a few of them have had their extensive towed array sonar equipment removed, including HMS Kent that I served on. And there's 13 of them active in the Royal Navy as of 2021. Well, what happened to the other 3? Because 16 were built? Well, the simple answer is we sold them to Chile. Why did we sell them to Chile? Well, probably because they were the dodgy ones. So we sold them, I think, 2 of the oldest and HMS Grafton, which was, again, not casting too many aspersions. It had issues, Grafton, and I think that we essentially gave them to Chile, albeit once we'd overhauled the main gearboxes on them. Again, they weren't designed to last a particularly long time, and they have lasted a particularly long time, so they're all pushing 30 now, and will be pushing 40 by the time that most of them are retired. So it's not a bad existence, really. Here is a picture of HMS Northumberland in December 2020, so it's a fairly new picture. Northumberland here has been updated with the new Artisan 3D radar on top. Obviously she's got the Mod 1 faceted 4.5-inch gun, and she's also got the Sea Scepter common anti-air missile system, which replaced the original Seawolf, so she's a pretty potent fighting machine. You'll also note that she looks pretty knackered. You know, you've got rust streaks, she just looks a bit of a mess. That, unfortunately, is a feature of most Royal Navy ships once they're actually set to work. The Royal Navy has a habit of really pushing their ships and, let's face it, people quite hard. We do much longer deployments than most other navies, and Northumberland here is probably doing fleet-ready escort duties, which means she can be bounced at any moment. So chances are, as soon as the buffer had got off to try and paint the side of the ship, he got bounced and off they went. But yeah, it's true that Royal Navy ships do often look a little bit shabby in service. They have a displacement of about 4,900 tonnes, so that is between the sort of BATS 2 Type 42 destroyers and the BATS 3 Type 42 destroyers, but significantly smaller than the BATS 3 Type 22 frigates. They've got a slightly shorter length than the BATS 3 Type 42 destroyers, and shorter than the BATS 3 Type 22 frigates. It's 133 metres, but they are wider at 16.1 metres. That allows them to have a fairly good seakeeping performance, and it also gives a bit more room internally. You'll notice the width here, especially on the helicopter deck, which is a nice big helicopter deck, which we'll talk about later. So that extra width on the Type 23s was a good design choice. Has a relatively low crew in comparison to earlier ships of about 185. It depends on the layout, but that's something like 100 less than on a Type 22 frigate or a Type 42 destroyer. And they have a speed of about 30 knots. That's with both gas turbines and all diesel generators running. Now, most sources will quote in excess of 28. I've personally taken a Type 23 up to 30 knots, but the speed that each individual ship can make will depend on its layout, how much fuel it's carrying, whether or not it's got the transom flap, which I think all of them do now, the anti-fouling system and so on, not to mention the weather. So I think, yes, definitely over 28, but I think a good one should easily get to 30. The max cruising range, about 7,500 nautical miles. I've put a plus there, and I'll explain why in a couple of slides. It's not because of replenishment at sea, although of course it's completely possible to replenish these things at sea, and we quite often do so. It is for another reason, but you'll see in a minute. And they can carry one Westland Lynx or Augusta Westland, which is now Leonardo, EH-101 Merlin helicopter. Now, the anti-submarine equipped ones, i.e. the frigates with the towed array sonar, they generally carry the bigger Merlin helicopter, which is a pretty good anti-submarine helicopter. Most of the other frigates will typically just have a Lynx because it's cheaper and smaller. But the ship can take either. Key features of the Type 23 class include some of the following. So the 2087 towed array sonar, this is fitted to 8 frigates. It's an update on the original sonar that was fitted, and it is an active passive towed system. The Navy is not supposed to use it in peacetime in active mode without conducting a quote unquote environmental assessment, but as far as I can tell that involves having Johnny Numbnuts on the bridge wing check that there's no whales around before pumping thousands of decibels into the sea. So I'm not a massive fan of using it in the active mode, but then again, if you're hunting submarines, you've got to do what you've got to do. As I said, it's got a very large flight deck, a nice big hangar, and if it's got the EH-101 Merlin helicopter, then you really are in business, because that is a good helicopter with 3 engines. Seawolf, originally anti-air missile, or the CAM missile system as we see here, both of which are relatively short range, almost point defence missile systems. They can't really offer much in the way of a fleet defence capability unless you're right up next to the ship that you're protecting. They've got the Harpoon anti-ship missile. You can just about see 2 of the canisters here in range. Now they carry 8 missiles in canisters on the bow, but I have heard on the grapevine that the Harpoon is no longer supported in the Navy, but I can't find an official source for that, and it's unlikely that I will either. I've no idea why they would remove it other than for cost considerations, but cost unfortunately drives a lot of these things, so it is possible that they're not supported and we don't know about them. In a similar way to the fact that sonars on older ships were put at quote unquote 180 days notice and so on. All I do know is that I can still see the canisters on front of Type 23s, so as far as you know, we are officially aware they are there and in service. Updated models have got significantly improved weapons and sensor fits, i.e. the Artisan 3D radar, the CAM missile, the 2087 towed array sonar, and they've probably had updates to the command system. And since 2018 they've started to receive updates to the power generation system. So these ships actually have received quite a lot of in-service support. They have a highly specialised combined diesel, electric and gas, or CODLAG propulsion system, which is on 2 screws with non-controllable pitch propellers, meaning that you have to stop the shaft and reverse them in order to go astern. And that's obviously something that we're going to be paying particular attention to in the rest of this lecture and in the following lecture. And they have very quiet operation. Now, these ships were primarily designed as anti-submarine warships, and therefore that noise requirement drove the design in pretty much every way. Now, pretty much everything that we look at on the propulsion system has been built that way in order to reduce noise as much as possible. But by reducing noise, you generally end up with an efficient system, so it has the side effect of having a long range and good fuel consumption, which I think these ships do, and they still stand up quite well today. Due to the beam and the highly flared bow, they've got good seakeeping. We've seen they've got a good top speed, and they're generally a good general purpose platform. These things do ride the waves quite well, and unlike older, narrower ships, they don't seem to suffer from cracking in the midships region. They've got good damage control facilities. As a result of experience gained in the Falklands War, the designs were modified, so they've got good damage control stations, plenty of DC equipment. They've got 5 high-pressure salt water pumps, built-in smoke clearance exhaust fans, built-in emergency generators and so on. They're actually pretty good in that respect. They've got an appropriate level of automation, I would say, remote control and SCADA, albeit obsolete. And so these vessels are computer controlled, but they're computer controlled based on early 1980s microprocessors, which can easily cope with the task they've been given, but what it does mean is that you don't have a highly complex distributed interactive system, and that, in my limited experience, tends to be where you get issues. So they are automated, but it's relatively easy to take manual control of things, and they're not automated so far that you are likely to experience serious issues, and certainly I never did. They're much better living conditions than the Type 42 destroyers, arguably for some ranks or some rates not as good as the Type 22 frigates, but that really depends on where you were on board. Certainly, as an officer, my living conditions on a Type 22 were better than on a Type 23, but that wouldn't have been the case for everyone, so I think they're probably similar. They're certainly much better than the Type 42s to live on. I'm going to look at a few disadvantages, but I've been a bit nitpicky on these, and all of the things I'm about to list could be argued the other way. I've just tried to do it in the grounds of fairness, really, because there is no such thing as a perfect ship, and a Type 23 is a long way away from a perfect ship. But they are pretty good for the size and the cost. And therefore, you know, all of the disadvantages I'm going to list here could have been sorted out, but they would have resulted in a more expensive and or bigger ship, which the Navy wasn't in a position to pay for at the time. Nonetheless, I think these disadvantages are relatively real. Here we'll see HMS Richmond from above. It's got the RM here on the flight deck, which is how I know that. And again, this is a relatively original yard spec with the Seawolf missile system, 996 radar. She's got the Mod 1 gun though. Most of the Type 23 frigates from the mid-2000s had that fit out. They had, I would say, relatively low levels of redundancy in comparison to earlier ships, particularly with mechanical plants. So for example, high pressure air compressors, they only had 2 instead of 3. Chilled water plants, they had 3 instead of 4 or even 5 on the batch 3 Type 22 frigates. And that was a trend really across most of their mechanical systems. And just to put that in perspective, if you lose your air compressors, you will end up in a situation where you can't start your engines. And if you can't start your engines, then you have very bad juju. Now, I've personally experienced a system whereby the same thing failed on both HPACs, which was the drive shaft of the water cooling pump. So we took the part off one HPAC and put it on the other, and then that failed, and I then had to substitute a drill pump in order to circulate water through this HPAC so that we could charge the air bottles sufficiently to continue operations, whilst we sent a bunch of sailors off on a seaboat to another Type 23 to rob their drive shaft. These idiots then came back with the wrong part and the saga continued. So yes, relatively low levels of redundancy. Clustering of weapons on the bow, this is not a problem that's unique to Type 23s, but it does somewhat irritate me. We've got a 4.5-inch gun, Seawolf missile system, harpoons, all clustered round the bow. On a Type 23, yeah, we have some small arms for midships, and we do have the Stingray torpedo launchers just forward of the hangar, but those, particularly the Stingray torpedo launchers, are really not likely to be that useful. If a submarine's got close enough that you're firing short-range torpedoes sideways at it, you've probably had your day anyway. Okay, the helicopters at the back end, which is a weapon system as well, and a very potent one, but in general, if you lob something at the front of a Type 23, it's gone. Now that obviously is the case on many warships, but an example that wasn't like that was the Batch 3 Type 22s, which had the gun on the front. They had Seawolf forward and aft twin launchers. They had harpoons amidships and goalkeeper amidships as well, so they were a bit more spread out, which I think made them slightly less vulnerable to losing all of their weapons in one go. They've got a high crew workload, so the reduced crew count actually means that on paper they're not going to be busy because of automation, but actually once things start wearing out, which of course they do, particularly in the cash strap, maintenance strap Royal Navy, crew ends up working pretty damn hard to keep everything going. I know that might seem like a strange statement to make if you're not familiar with warships and how they work, but take it from me, the crew on these things are pushed really hard and they're frequently knackered. I mean, I thought I worked hard on a Type 42 destroyer, but when I went to a Type 23 it was murderous. They don't have a gun-based close-in weapon system. They relied on Seawolf for its replacement, so Seawolf is pretty good in the short-range area. It is, after all, a short-range weapon, and it's been combat proven in the Falklands. But I still would rather have, in addition, had a gun-based close-in weapon system like Phalanx, or better yet, Goalkeeper, to handle with anything that got through Seawolf. Because although Seawolf was combat-proven in the Falklands and did shoot down real airplanes carrying real people, I've only seen it launched twice, and on both occasions it missed a towed target travelling at only 300 knots in a known position, so I'm not sure I'd want to rely on it. Inferior but sufficient manoeuvrability in comparison to CPP vessels. This really is a nitpicking subject, because actually the reason that it has non-controllable pitch propellers is for noise reduction and efficiency, and it's very good at that. The disadvantage is that you need to stop the shaft and reverse it to go astern. Now that takes several tens of seconds, I'm not going to tell you how many, whereas on a controllable pitch propeller system you can simply reverse the pitch in about 3, 4, 5 seconds and the ship's going full astern. Now mostly that will be a disadvantage. In day-to-day operations, the only disadvantage of that is going to be in docking. Now a good captain can still get one of these things in without a tug, but generally we'll have a tug anyway because they don't have bow thrusters. In normal service, sort of crash stops, astern movements are not that common anyway, so the disadvantages of that reduced manoeuvrability are significantly outweighed by the advantages of not having a noisy CPP system with oil moving around the shaft, with inefficient propeller blades with a big hub and all the associated pumping noise. My personal opinion is that they had a very variable build quality, particularly I got the impression that the later ships were thrown together in comparison to the earlier ships. The later ships are obviously a lot cheaper, although you could say that that was because the shipyards had got better at building them, and I'm sure that that takes up a lot of it. But in fairness, you know, the actual build quality, when you look at weld finishing work and how pipes were constructed and held together and so on, it did seem to drop off on the later ships, and that really did get on my nerves a bit. A bit of a controversial one, less stable at low fuel loads. Type 23 frigates had non-compensated fuel tanks, and what that means is that as the fuel got burned, air goes into the tanks. Well, that's exactly what fuel tanks are, you think, and most of the time it is. But on older warships like the 42s and 22s, they had what's called compensated fuel tanks. So what that meant was that as you burned the fuel, seawater entered the bottom of the tank and the fuel floats on the seawater. So as you consume your fuel, the ship actually gets slightly heavier because of the relative density of seawater and fuel oil. That has advantages in terms of the stability of the ship remains relatively similar throughout the fuel burn cycle, but it has disadvantages in terms of the fact that you have to clean the fuel from the seawater all the time, and in addition, because the fuel tank is open to the sea, when you are fueling the ship, you have a reasonable chance of overfilling the fuel tank with fuel and pumping the fuel into the sea. And in fact, this problem got so bad when I was a junior officer in Plymouth that it was decreed that we were no longer permitted to refuel our ships alongside in Plymouth, and we would have to go to sea and replenish at sea. Not because that reduced the chance of us spilling fuel, but because it reduced the chance of anybody noticing that we were spilling fuel. The ships have to carry a certain amount of fuel in certain fuel tanks in order to maintain an adequate level of stability. I am not going to tell you how much fuel, and I am not going to tell you which fuel tanks. I will also tell you that the 7,500 nautical mile range is taking into account the fuel that you can burn. Therefore, when I put a plus beside the 7,500 miles, what I meant was that that range could easily be extended if you burned the fuel that you are supposed to not burn in order to maintain your stability. Now, there's two ways you could do that. One is you can burn it and you will probably be fine. Two, you could transfer that fuel to another fuel tank and fill the fuel tank whence it came with seawater. Now that's kind of a one-shot stop, but it would totally be possible. Certainly something you could do in an emergency, for example, if your tanker got hit in a war. So that option is there to increase the range of these things quite a lot. And so that less stable at low fuel loads, you could almost argue, again, is a bit of a feature rather than a bug. Okay, let's look at the main propulsion layout now. So, I'm going to read the bullet points and then I'm going to take you through this diagram. The fish I was not expecting. As I said, we've got a cod-lag system, combined diesel, electric and gas. This is based on two reversing shafts. Ahead, the shaft can be driven by an electric motor, as seen here, propulsion motor. or by a combination of a propulsion motor and, via this gearbox, a Rolls-Royce Spey SM1C gas turbine, and that is an option on both shafts. It is possible, if your propulsion motor or one of the links in the chain that feed to it has failed, to drive a shaft in the forward mode only with the gas turbine only and without the propulsion motor. However, if you're going to do that for a long period of time, you need to lift the brushes, which we'll look at in part 2. Astern, the shaft can only be driven by the electric motor. That means that if your electric motor on a given shaft, or one of the links in the chain that leads to it, has failed, you will not be able to go astern on that shaft. Unfortunately, that is a situation I have been in, and we ended up scraping our propeller blades outside Plymouth Sound one very stormy night. Because the CO decided to do a completely unnecessary crew transfer when our port shaft converter had failed and we couldn't go astern, and we had a brand new navigator. So that was very exciting. Okay, having read the bullet points, let me get my pen out and talk you through what we've got here. We have got on each shaft a Spey gas turbine, which is about 12 megawatts each, and they're obviously powered by diesel. That Spey gas turbine drives through from the gas turbine room here, which is on the right, into the motor gear room, or MGR, on the left. And the motor gear room is probably the busiest mechanical compartment on the Type 23s, even though compared to, say, a Type 42 destroyer, as we'll see in a minute, it's nice and roomy. Inside the gearbox we have a double reduction feature, and that obviously, I've drawn it wrong but never mind, has a clutch, which we'll look into in part 2, that drives the main shaft, and that shaft goes through the middle of the propulsion motor all the way back down to a 5-bladed prop. At the front end of the gearbox, or the rear end of the gearbox, pardon me, there is a thrust block, and that job of the thrust block, which I'm going to write here, thrust block, is to transfer the force which is generated from the shaft with a propeller into the ship. Now, the thrust block is the only part of the gearbox that moves when the ship is in electric motor drive. Okay, so when the ship is not in electric motor drive, when it's in gas turbine drive, then the gearbox will rotate. Otherwise, the gearbox will be stationary, and the reason for that is noise. We also do not use forced lubrication pumps unless the gearbox is turning, and that means that the thrust block has its own special splash lubrication system. All well and good, I hear you say, but Ollie, where does the electric power for the propulsion motors come from? Good question. We have got 4 in number diesel generators, which I will show you a picture of in a few slides. Each one of those diesel generators has a power of approximately 1.3 megawatts. Okay, so we have 4 in number diesel generators, and each one is 1.3 megawatts. Times 4, and they provide power at 600 volts and about 62.4 hertz to a 600 volts 3-phase bus. Now, that 3-phase bus provides power to the converter regulators. There's one thyristor converter regulator per electric motor, and that drives the propulsion motors. There's also in there also a field regulator because the motors are separately excited, but we'll look into that in part 2. Now, you're going to ask me, why are we using a slightly odd frequency of 62.4 hertz? And the answer is that unlike other ships which we've looked at, the electricity generation for propulsion and the electricity generation for domestic uses come from the same diesel generator. So the 4 diesel generators do both the ship's domestic service and the propulsion. Domestic services on a ship require 440 volts at 60 hertz AC, as we see here on the output bus. Now, 60 hertz is not the UK standard frequency, which is in fact 50 hertz. However, the UK is a NATO country, therefore all NATO warships use 60 hertz as a standard frequency, so that we can all use each other's source supplies, portable generators, and so on. In order to achieve a very stable 60 Hz frequency, which is needed for things like the radars, etc., we are using 2 motor generators, and each one of them is 900 kilowatts. And those motor generators transfer the 600 volt 62 Hz into 440 volt 60 Hz. And the reason that we have to have a slightly higher frequency on the input is because there will always be a certain amount of slip in the induction motors in the motor generator. Why did we use a motor generator instead of static frequency converters? Static frequency converters certainly were available at the time, and were available decades before, in fact, but the main reason that motor generators were selected, as far as I can tell, is for harmonic distortion reasons. So we didn't want a series of harmonics in the domestic supply, and at the time that might have been difficult to practically filter out. It would be possible now. Likewise, the thyristor converter regulators are 4-quadrant converters, and they are much larger than the equivalent on, say, an electric locomotive. And one of the reasons that they're much larger, even though they're not particularly powerful, is because of the amount of harmonic filters that they had to have. Because the last thing you want is to inject harmonics into your propulsion motor and then your shaft, where every submarine for 1,000 miles is going to hear you. So this layout has really been primarily designed to be as quiet and harmonic free as possible, to the extent that it is using equipment that most of us may well consider to be fairly outdated at best or obsolete at worst. Now, it is very likely that these motor generators either have been or will be replaced in future, thanks to advances in things like IGBT, static frequency converters, but I'm not sure on that. The propulsion motors are DC brushed motors, and we'll look in them in more detail in part 2. So, to summarise, Spey gas turbine driving a gearbox, gearbox driving through the propulsion motor, a hollow, no-nonsense shaft with a fixed pitch propeller. In a stern mode, only the propulsion motor can give you that, and we power the whole thing by diesel generators. We run typically anything from 2 to 4 diesel generators, depending on how fast we need to go. In principle, 1 diesel generator is capable of providing a hotel load for the ship, but we never really operate with just 1 diesel generator, because if it falls down, the ship would experience a total electrical failure, which is bad. So in practice, we use a minimum of 2 diesels, and we only have a maximum of 4. Looking along the shaft line of the main propulsion system, here we see the gas turbines in the gas turbine room. Now, this is looking aft, so behind this bulkhead at the far end is the motor gear room, which has the gearboxes and the electric motors in it. So here we have on the starboard side, or on our right hand side, which is the port side of the ship, we have a Spey gas turbine module, same on the other side, which is the starboard side of the ship, our left as we look at it. As you can see, similar to the Type 42 destroyers, the modules are fully enclosed spaces with a door to go in, which you should not go unless it's an emergency or the engine's shut down or you have MEO's permission. We have the fire suppression systems for the modules at the end. It's not quite as toxic as the system fitted to the Type 42s, but you still don't want to breathe it. At the foreground of the picture, we have the local control panels. Here in local mode, you can start, stop and adjust the speed of the gas turbine. You would have to do this obviously if you're at action stations and you'd been hit and the control system had been damaged. We also have these stainless steel tank arrangements, which are for the compressor cleaning equipment. Looking back again, we see a set of bellows between the uptake, the exhaust uptake for the gas turbine, and the main ship's exhaust uptake. That permits expansion, yes, but more to the point, all of these things are mounted on resilient anti-vibration mounts to attempt to limit the transmission of noise and vibrations to the ship's hull. Obviously, there's no way you can run a gas turbine without making a lot of noise, but the designers have tried, nonetheless, to minimise that noise as far as is practicable. Down here on the ground, we've got some toolboxes all stowed in. I will guarantee that whatever tools are supposed to be in those toolboxes have gone walkabouts, because that's just what happened. And we have a small damage control locker. This ship is a generation ahead of the Type 42 destroyers, so even the local control panels are computerized to a certain extent, and there are no physical Bowden cables going down to an engine trip module. That's all has to be done either locally or via this electric control panel. For that reason, it is actually a lot easier to operate these engines in the local mode than on the older ships, and actually it's quite difficult to damage them, for example, when starting them locally or when operating them locally. One of the most likely failures you would make is forgetting to turn on the fuel boost pumps to high speed, but again, we'll talk about that kind of thing in part 2. As you can see, there's quite a lot of room in these ships, certainly in comparison to the Type 42 destroyers, mostly because they're beamier, and that really did make them a lot more pleasant to work in. Here we are looking at 2 of the 4 diesel generators on board. Now, connoisseurs amongst you will note that these are obviously the upstairs diesel generators. Of the 4 diesel generators, 2 are upstairs above the waterline and 2 are downstairs below the waterline. Again, the concept of mounting the diesel generators above the waterline was to reduce noise as far as possible. In practice, because the downstairs diesel engines are mounted in acoustic enclosures, they would typically have a slightly lower noise signature than the upstairs diesels, but nonetheless the concept was there. The reason I'm showing you the upstairs diesels instead of the downstairs diesels is for that exact same reason, that the upstairs diesels are not surrounded by an acoustic enclosure and therefore we can see them. Now, these are 12-cylinder V12 Paxman Valentia engines, made with pride and loving care in Colchester in England. If you have heard of Paxman, and if you have heard of Paxman Valentias, it may well be because of the Intercity 125 high-speed trains in the UK. Now, these trains are very successful and still operate and are still the fastest diesel trains ever built anywhere in the world. But they were built from 1976 and they used these very same engines. Now, the ship that I'm showing you a picture of here left the yard in 1998, which is 22 years after the first HST rolled off the production line. So it is completely fair to say that Type 23s used obsolete diesel engines. Now, at the end of the diesel we have the generator here, and these are brushless AC generators, which are again pretty good. They're similar to what we used on older ships, but they're very reliable and not a problem. The diesel engines, on the other hand, were a constant source of worry and woe, and there were many reasons for that. I believe that Paxman, generally speaking, designed a good engine for the purpose with which it was intended, which was to operate railway trains. In the UK, due to the very small loading gauge of our railway system, you need very compact engines, and Paxman essentially promoted compactness and power above everything else, including reliability and maintainability. And that wasn't so much a problem for high-speed trains because it was relatively easy to drive the loco into a shed at the end of its working day, lift out one engine, drop in a new one, and then send the defective engine to a factory for repair and overhaul, and that's exactly what they did. Unfortunately, mainly due to the cheapness of construction of Type 23s, it was not an easy job to pull an engine. You had to cut a hole in the deck. So we had to do the vast majority of the maintenance on site, and these things were not easy to do. In addition, they didn't like operating in hot countries, and they didn't like operating at variable loads, which was all the sort of things we used to do on a warship, particularly when we were patrolling, you know, with forever turning off chilled water plants, high pressure salt water pumps, coming up and down in speed, turning on and off radars and so on, running the diesels at low loads for very long periods of time. All that took a big toll on them, particularly in the temperature scatter, and we used to get head gasket failures relatively regularly as well. In addition, the things were prone to oil leaks, and they weren't the best consumers of diesel, although they weren't too bad. Another feature, if you like, of the upstairs diesels is that they need cooling. So although the diesels themselves are cooled by a freshwater loop, that fresh water is cooled with a seawater freshwater intercooler. And for the engine that is on our right, which is actually the starboard engine because we're looking forward anyway, that cooler is underneath the gangway that we're standing on. For the engine that is on our left, the cooler is further to the left out of shot. Those coolers receive water from the low pressure saltwater system, which is a feature of Type 23s that's quite good. That essentially circulates low pressure salt water to various pieces of machinery that require cooling, rather than relying on the high pressure salt water system, and that leaves the high pressure salt water system free for its main job, which is firefighting. In an emergency, the two can be cross-connected. The downstairs diesels have their own built-in gear-driven pumps which suck water directly from the sea, but they can be connected to the low-pressure saltwater system in an emergency. Thus, in the event of a total electrical failure on a ship, you are going to have to start your downstairs diesel engines first, because you will not be able to provide power to the low-pressure saltwater system to power up your upstairs diesels, although of course you could still run them for a few minutes without any cooling, so you probably could do it if you absolutely had to. So much for the diesel engines. The next thing is the gearbox. I'm not going to talk about the gearboxes that much. We'll look at the gearboxes much more in part 2, but the main point that I'm making about the gearboxes is that they don't actually rotate unless you are in gas turbine drive, or you have had an emergency and the clutch has locked in and won't come out, and you need to go either ahead or astern under EM drive. And the reason for not turning the gearbox is noise. So not only do you have the benefit of not spinning the gearbox and making lots of noise, you also have the benefit of not needing to run forced lubrication pumps, not needing so much coolant for the oil that would be running through the gearbox, and so on and so forth. Because of the fact that the gearbox must not turn unless the gas turbine is on and selected, the clutch mechanism on the gearbox is more complicated than it would be on a Type 42. In addition to the fact that it's more complicated because it needs to be controlled in and out rather than a simple sort of ratchet concept design where you spin up the engine and it locks itself in, the clutch is also on the output side of the gearbox, which is the high torque side of the gearbox. What that means is that the clutch is physically much bigger than it would be, or is rather, on the Type 42 and Type 22 type ships, and it's more expensive. But that is the price that we've had to pay in order to have a gearbox that does not rotate unless the gas turbine is running. Again, because the gearbox isn't designed to operate all the time, they have cut corners on it and made it significantly cheaper. So the main secondary pinion rather, and the secondary wheel, which is the one that we see here being pulled, are only single helical, not double helical, and that means that there's thrust blocks in there and thrust cones, and they wear out, and we had issues with flank wear and so forth. So there isn't a Type 23 in existence that hasn't had its main wheels pulled at least once, possibly twice, for repairs, and it is a drawback of them, and that was all done really, in my opinion, as a money saving trick. So instead of being built by David Brown, these gearboxes were built by GEC to a significantly lower specification, and that really did show. Nonetheless, they did achieve their main job, which was to be quiet. We'll look in much more detail in this in part 2. Here's a quick diagram of the shaft. Feel free to pause this presentation and examine it at your leisure. It's very similar to what we saw before on other ships, except that the hollow shaft does not contain any oil or push rods or pipes or any of that in it. It is literally just a tube, which is simple. At the back of it, we've got a 5-bladed Type B high skew noise reduced propeller. We have the after A brackets and bearing and the forward A bracket and bearing, which support the weight of the shaft outside the ship. We then have the oil injected SKF coupling that I mentioned before, which is something that you should Google if you're interested in it, because I think they're a fascinating piece of machinery, and that allows us to separate the shaft and pull it out the back of the ship without having to remove the internal section of the shaft from the ship. We then have our ceramic water lubricated face seals, which are excellent, and we have a plumber block which supports the weight of the shaft and prevents it from sagging. We then have a flanged coupling where we go to the forward intermediate shaft, which goes through a single bulkhead gland into the motor gear room. Here in the motor gear room we have a disc brake mounted on the shaft. We've also got a torsion meter, which I haven't shown, I don't know why, and a second plumber block. We then have another flange coupling and we go through the propulsion motor. Now, What is not shown on this drawing that I drew many moons ago and should be is the final sort of thrust block that is part of the gearbox that is on the right hand side. And I really should have included that in this drawing. But a key point is that the propulsion motor surrounds the shaft, and the shaft is in several sections, and it is a nice simple shaft. It's approximately 400 millimeters in diameter, so it's a relatively chunky piece of machinery. I am not going to tell you the rotation speeds of the shaft, but they are fairly slow, as you would expect on a warship that's designed predominantly for anti-submarine operations. Let's look quickly now at some of the noise reducing features of the Type 23 frigate. Hopefully you've probably figured out a lot of these for yourself by now. So they've got the noise reduced fixed pitch slow turning propellers, which is key to the way they operate. And by having a fixed pitch and not a controllable pitch propeller system, it means that among other things you can have a narrower hub, which generally reduces the amount of turbulence that you're going to have in the water. We have the diesel electric propulsion system, which has gearboxes disconnected in electric motor drive, which allows for a very, very quiet operation indeed. The forced lubrication system is not required in electric motor drives. Shaft and the thrust block are lubricated by an oil bath, so that means that the FL pumps are not required, and that again has a consequent reduction in noise. We have the upstairs diesels above the waterline, so they won't transmit noise directly into the water, and the downstairs diesels are in special enclosures. In fact, in the downstairs diesel room you can have a conversation beside two running diesels like we would in normal life. You don't need ear defenders. It is remarkably quiet down there. All the key equipment is double mounted and rafted on resilient mounts, so that the idea is that it can't transmit vibration. We have masker air belts, which I have always been a little bit dubious about, but we can pump compressed air out of little holes on the side of the ship, and the idea is that that somehow masks our noise signature. I'm not convinced how well it works, but I'm also not an expert on these things. All I know is that the masker air compressors on the ships that I operated were never really tested. The book claims that there's cascade plates in HP fluid systems, which is supposed to reduce the amount of turbulent flow, for example, around sharp bends and stuff. There are a few of those. They're not widely used, but they do exist and they do help. They've got 2-speed fuel boost pumps, so what that means is that for diesel generator operation we'll only use the fuel pumps in the slow mode, and we'll only turn them to fast mode if we're using a gas turbine, so again that reduces the noise quite considerably. And we have a built-in hull vibration and monitoring system. This has transducers around the ship which are bonded onto the hull itself, and they are capable of conducting spectrum analysis and fast Fourier transforms of the actual vibration that the hull is experiencing in order to allow us to assess what our noise signature is and hunt down any areas of concern. And it is quite a good system if it's used correctly. Certainly on the Type 23s, which are still fitted for anti-submarine work, that is a system that is going to be extensively used and people will be all over it. Just as an aside, if you are wondering if this drawing I made is of anyone in particular, yes it is, and the individual involved knows about it. There are clues as to who it might be from documents that I've scattered around the drawing, but he was a good guy, I liked him. Let's look now at fuel consumption and performance. So, the speed and the fuel consumption depends on the engine state that we've got. So if we're in 2 generators with electric motor mode, we'll get a speed of around 14 knots, and that will be power, and this power, by the way, is the electric motor power, not the diesel generator power. So the power in the electric motor is 1.5 megawatts, because remember the remainder of that power is going into the ship's hotel load. and that gives us a consumption of around half a ton an hour. Now on a Type 42 destroyer at about that speed, you'd probably be looking at around 1.5 to 2 tons of fuel an hour to achieve that, by the time you've accounted for the diesel generators and the boilers and evaporators and the tyne engine that you'd have to have running. So we're significantly more efficient than that. 3 diesels, EM mode, you get about 15 knots, you've got about 2.25 megawatts on the shafts, and you're burning about 0.75 tons per hour. That would be a fairly typical transit mode. 4 diesels would be nice, but in my day that was almost never possible because one of our diesels was almost always broken. We very rarely had all 4 available. But in the exceptional event that we did, you'd get about 16 knots, and that would be 3 megawatts of electric power on the shaft, burning approximately 1 ton of fuel per hour. So again, that really isn't a bad rate of burn for a relatively large ship, particularly something as specialist as a warship. Sided boost is a mode where you have gas turbine and electric drive on one shaft and electric drive only on the other. Now, in principle, the speed that you achieve on sided boost would depend on whether you had 2, 3 or 4 diesel generators operational, but in practice it doesn't make that much difference. Since one gas turbine is about 12 megawatts anyway, it completely overpowers the electric motor. So I've just put sided boost, it's about 24 knots. And that's 15.5 megawatts if you had all 4 diesels running, or about 5 tons an hour. And now again, a Type 42 destroyer at 24 knots would have at least 1 Olympus running, which is 6 tons an hour. It would also have all its boilers and evaps running, so that's possibly another ton an hour. So you're looking at 6 to 7 tons an hour. And if it was an old one that was struggling a bit, you might need a tyne as well. So you'd be looking at 7, 8 tons an hour. So it's a bit better, but not much. But that's because of the speeds involved. Both gas turbines, all diesel generators, everything you've got. I've put 29 knots because I'm pretty sure most 23s now will achieve that. But as I said, I got 30 out of mine. And you've got about 28 megawatts being dumped into the water. So now your consumption's relatively high, something in the region of 9 tons an hour. Again, a Type 42 at that equivalent speed is going to be burning about 12, maybe even 13 tons an hour, depending on the specification. So we are definitely better. It is possible to lock a shaft, but I can't really remember what speed you can achieve with a locked shaft, and the power will depend and the fuel consumption will depend and so forth. I mention it only in the fact that you can do it. The Type 23 we see on our left here is doing a high-speed overtake of the Type 23 on the right, and you can actually see that although it's ploughing headfirst into the sea, it's actually maintaining a fairly dry foredeck, and that is a result of that heavily flared bow. It's just an example of how these ships are pretty good. Incidentally, the Type 23 on the right has got the original Mod 0 4.5-inch gun, so that kind of dates this photograph a little bit. I've got a couple of notes here. As I said before, if an electric motor or its converter fails, that shaft cannot be spun in reverse. There's no way to make it go in reverse except to drag the ship backwards through the water, which if you were to do that, you would definitely want to lock that shaft. Equally, if an EM or converter fails, the brushes should perhaps would be better, must be racked out to operate that shaft in gas turbine mode. So otherwise what will happen is the brushes will just get worn out as there won't be any current going through them, and they'll just sit there on the electric motor, which is being driven by the gas turbine. It is a relatively simple matter to rack out the brushes. It only takes a couple of hours, and we use the power of cable ties to keep them off the motor. But it's something that I've done, and it's not a big deal. But you can get away with it for, you know, minutes or maybe even hours without racking out the brushes. But you definitely should do it if you've got a long-term defect. Okay, just a quick summary then. So the Type 23s had a specialised, quiet and efficient propulsion system, and they really did. Everything about that propulsion system was designed to be quiet, and that is the reason that it is what it was. I would say they weren't as well built as previous ships. In particular, their gearboxes were quite cheap and nasty, and all of them experienced problems at some point in their lives. But they have been upgraded and improved in service, and they continue to be. The Navy's made quite a big commitment to improving the Type 23s and keeping them working. They are economical, they're adaptable, they're flexible warships. And in part 2, we're going to look in more detail at the electric motor system, the gearboxes, the gas turbine changeover and the stern propulsion, and I'll do my best not to make that too long-winded. In summary from point 1, I would say that these are good warships. They're not perfect warships, but I certainly think for the cost they deliver a lot more than you might expect from something as cheap as they are, and they certainly stand up very, very well in comparison to anything else that was made in the same era, particularly in terms of damage control. With that, thank you for watching. Again, if you have any comments or corrections, put them in the comments box below, and please join me for part 2, where we will look in more detail at the operation of some of the equipment that we've talked about today. Thank you very much, and good day.